Hello, can you hear me? Can you hear me?
Yes, sir.
Okay, fine. I'll keep it muted. If somebody wants to ask, I can unmute and answer.
Okay, sir.
म्यूट कर दो तो शायद हमने कहा क्या होगा म्यूट
सही है।
यार तो एक बार पढ़ा तो नहीं है तो
अरे पिघले स्टार्ट।
हमें ये फाइनेंशियल ईयर अपन
So yeah, I'll try to answer the question. So the question is, can we say the same about the spectrum of adjoint of an operator, right? Um, yeah, but can you be more specific? Are you talking about how the spectrum of an operator and its adjoint are related? Okay. So this,
Hello, sir.
yeah.
I was just asking that if we have a bounded linear operator, then
Yeah.
what can you say about its like spectrum of its adjoint?
Yeah, so there is something called the spectral mapping theorem, which we probably covered in the course. I don't know if you have reached that part. So that will tell you that for appropriate functions, the spectrum of, so if f is a suitable function, the spectrum of f of t is the image of the function, image of the, so it's like f of spectrum of t, right? So this is like what you said, what you see in the linear algebra situation, finite dimensional operator, right? So if A is a matrix and lambda is an eigenvalue of A, then lambda square will be an eigenvalue of A square, right? Or if I take a polynomial in A, then let's say P, then P of lambda will be an eigenvalue of P of A, right? The same, of
Yes,
course,
sir.
the same happens in the case of uh, infinite dimensional operator as well. You have to be a bit more careful about the spectrum is closed and so on, right? So there are certain issues there that may come up. But we have a neat spectral mapping theorem, which we will, in fact, it will be done in the course as you go along. So, but it may be slightly early to understand it now. So if I start with a element x in a Banach algebra, right? Then so let's say Banach star algebra or a C star algebra, then depending on certain properties of x, one has the spectral mapping theorem, which says that the spectrum of x and x star, how they are related. So this would be just taking the complex conjugate, and that, so this is true in general, and it would be applicable in sister algebras and in particular for operators. Okay. So wait till spectral mapping theorem is proved. Maybe that will answer your question in generality.
Okay, sir. Thank you,
Yeah.
sir.
So there is a, I missed the submission. Yeah, if the deadline is passed, then the submission is no longer possible. Yeah. Okay, let me try to answer that. The term operator simply means it is a map from vector space to another vector space. It's a linear map, which is a vector space to another space. Resolvent operator is a linear map. It is no, so when I say resolvent operator of let's say of T, it is the inverse of T minus lambda or T minus lambda times identity. And that is a linear operator. It is a linear operator on the same Hilbert space, right? It is not linear in lambda, but it is as an operator, T minus lambda I is a linear operator. Its inverse its inverse is also a linear operator. Yes, you can unmute and ask Shailendra Pradhan.
Yes, sir. Thank you, sir. Sir, in the Gelfand transform,
Yeah,
this is basically our mapping from our Banach algebra to maximal ideal space. But
yes.
this maximal ideal space, sometimes finding this or getting idea about this will be difficult, right? Like it can be empty sometime or
Yeah, so that will depend on what all structure you have on your Banach algebra. In fact, that is why, so we start with a general definition of Banach algebras and we put more structure on it. So the basic example you should always keep in mind is a class of operators on a Hilbert space. Look at all bounded operators on a Hilbert space. That has so it is a vector space. It has a norm, and it is also a Banach algebra, right? Norm of T times S is less than or equal to norm T times norm S. There is a star operation, T going to T star, which is the adjoint of T. And the last one, which is special to certain class of algebras, is that norm of T star T equal to norm T square. That is the C star identity. That is the C star algebra identity. So if you have a C star algebra, which means that there is this star operation and you have the C star identity, which is norm of x star x equal to norm x square, then the Gelfand transform is very nice. Okay, that is one of the things we do in this course, right? The Gelfand transform becomes a isometry if you have identity as well. And if you have a commutative C star algebra with identity, then it is extremely nice because then you can identify the C star algebra itself as continuous functions on a compact Hausdorff space. And the isomorphism is the Gelfand transform. And the maximal ideal space then becomes just the space on which it is realized as continuous function. So if it is realized as C of x, where x is the compact Hausdorff space, maximal ideal space is x itself. Okay, it always sits inside the unit ball of the dual. So there is some structure, but depending on the Banach algebra you are looking at, identifying it as something which you can work with can be a difficult problem.
so in this structure, our identity and unit and commutative, these things play a very important role. Mm.
Yes. So at least in the first part of the course, that's what we do, right? We look at commutative C-star algebras with identity and prove that they are continuous functions on a compact Hausdorff space. Now, if you remove the identity, that is like removing a point from the space. So then it becomes locally compact. So instead of compact, so think of the compact space, for example, the circle in R2. You remove a point, it's something like the real line then, right? It is a locally compact Hausdorff space. And your C-star algebra will be identified as continuous functions vanishing at infinity. The infinity is the identity essentially, or the Gelfand transform of the identity. So you are looking at continuous functions vanishing at infinity, and that will be your commutative C-star algebra. So this tells you about commutative C-star algebras. Commutative C-star algebras are continuous functions on a compact Hausdorff space if you have identity, or continuous functions vanishing at infinity on a locally compact Hausdorff space if you do not have identity. There is a non-commutative version of it which we did not cover in the course. Is that you can identify any C-star algebra as a closed subalgebra of bounded operators on a Hilbert space. So if you look at all bounded operators on a Hilbert space, then of course it is a C-star algebra, not necessarily commutative. And if I take any C-star algebra, that can be realized as a subalgebra, closed subalgebra of bounded operators on a Hilbert space. So that would be the general result, but we didn't do that in the course.
Thank you very much, sir.
You can look at a book by Diximir titled Sister Algebras. I'll just type it in the chat. But this book will have a lot of stuff. But it starts from very basics and goes to quite advanced. And for whatever we have covered, you can look at the first chapter of book by Folland titled Abstract Harmonic Analysis. So I'll type that as well in the chat. First chapter of abstract harmonic analysis that has everything about commutative sister algebras, and that is what we did. Yeah, I think we can stop the session.
Okay, thank you, sir.
Yeah, all right. Yeah, I'll leave.